Welcome back, episode 8. In this episode, we're going to jump into a little math. Very simple math. Multiplication and division, that's it. It's actually algebra. What makes it algebra is that we have variables, we have an equation or equations, and Ohm's law has 12 equations, a dozen. But you can determine most of the equations if you know just one or two of them. You can transpose and create the others for your work. So this is the first thing that you're going to really have to learn and memorize in a sense, and that is Ohm's law. So we're going to jump right in here and start talking about it. I don't have any script. I have some images that I'm going to bring up with Tinkercad, and we're going to work with those and see where it goes. So let's jump in and have at it. Okay, we have 3 images here. This one over here is Tinkercad, and we can start the simulation. We can get meter readings. Over here we have 2 representations of Ohm's law. This is the complete set of Ohm's law up here, and this is just one of them down here. So if you look at this one right here, you have volts, ohms, power, and amps. So really it's amps, watts, ohms, and volts. So you can calculate these values based on whether or not you have these values. So we'll drop down here to make this simple. The Ohm's law triangle. Now if you're learning this and you don't already have this memorized, then you need to stop the video, get a pad of paper, and write this down. Draw the triangle, just like it's shown here with V for voltage, I for current, and R for resistance. And if you have this triangle memorized, then notice that voltage equals I times R. They're next to each other. See? Voltage equals I times R. I, the current, equals the voltage divided by the resistance. We showed you this in a previous episode where the pressure and the resistance, as far as current flow goes, is directly proportional to the voltage. More pressure, more current. But it's inversely proportional to the resistance. So if the resistance goes up, the current goes down. So over here is current equals voltage divided by resistance. And as you increase the bottom half of this dividing here, if R goes up, then I goes down. Let's say that this was 1 over 1, and then it went to 1 over 2. Well, 1 divided by 1 is 1. 1 divided by 2 is 1/2. 1 divided by 3 is 1/3. So you can see as resistance goes up, the current goes down. Then the third equation is the resistance equals the voltage divided by the current. So voltage on top here equals I multiplied times R. But current equals voltage divided by resistance, and resistance equals voltage divided by current. So you need to write down this triangle and write down these 3 equations so you can memorize this. Now these 3 can be found up here. See, volts equals I times R. I equals volts divided by resistance, and resistance equals volts divided by current. So all 3 of these are up here in this major diagram. But you see there are 3 equations that you can use to calculate the volts, 3 for calculating current, 3 for calculating power or watts, which we've not talked about, and 3 for calculating ohms or resistance. But you see some of them are a little bit more involved. So these 12 include 3 each for these 3 factors. But let's stick with this one down here for now. So I'm going to minimize that. I'm going to bring up a calculator so we can do some calculations. So let's try something. I'm going to start a simulation, and across, you could say across the batteries, I have 2.94 volts, okay? And it results in 61.2 milliamps. Now, milli is 1 thousandths. So in order for you to do your math, you're going to have to move the decimal place over 3 places to the left. So it would be 0.0612. Milliamps is a way of making it easier to express thousandths of an amp. So this is 61.2 thousandths of an amp. The voltage is 2.94 volts. So if I go over here in my equation, and remember we're going to do R equals ohms equals voltage divided by current. So we're going to take the voltage, which is 2.94, and then we put in the symbol for division, which is a slash, forward slash, and they're going to divide that by 61.2 milliamps. But we're going to write that as 0.0612. So 0.0612, see the decimal place is moved over 3 places. So it would be 0.0612 amperes. But it's written in milliamps because that's the way it's displayed on the meter. The meter doesn't have enough positions to put 0.0612. So it has to move the decimal place over and then make it milliamps. So let's hit equal and see what we get. Okay, we get 48.039 ohms. So I'm going to go here to my note, and I'll have to stop the simulation and write in 48.39 ohms. Okay? So according to our Ohm's law calculation, if we divided the voltage by the current, 2.94 over 0.0612, we get 48.39. Now, all these other decimal places are wasted, so we don't care about those. Now we're going to go to the next one down here where we have 3 batteries, and we're going to do the same calculation again, except we're going to use 4.36 divided by 0.0909, because remember, 90.9 milliamps, that's 90.9 thousandths of a milliamp. So we've got to move the decimal place over in order to use it here. So we do the equal and we get 47.96. We'll round it off to 5. So I'm going to stop the simulation because it won't let me add the note. 47.965. We don't need that many decimal places, but we did it. Okay, now what do you notice about those two? Now, first of all, the only resistance that we are actually considering is the light bulb. Okay, and you're probably looking at that and saying, well, in the upper one, the light bulb calculated out as 40.039 ohms. But in the one with 4.5 volts, same light bulb, it calculates a different resistance. That's because of the temperature coefficient of the filament in the light bulb. Almost all materials that will conduct electricity have a temperature coefficient. If it's a positive temperature coefficient, then the resistance goes up with temperature. But in this case, it went down, right? Wouldn't you say that 4.5 volts is going to make the light bulb hotter, increase the filament temperature higher than 3 volts, right? And the resistance went down, which means it has a negative temperature coefficient. So kudos to Autodesk and Tinkercad here for making this realistic. First of all, they allow the measurement by the meter to respond to the internal resistance of the batteries. So remember, we didn't get 4.5 volts like the batteries are rated. We got 4.36. Now, let's say we wanted to measure the resistance of that light bulb with an ohm meter. See, this is an amp meter, this is a voltmeter, amp meter, voltmeter. So we'll stop the simulation. I'll grab this light bulb, Control C, Control V. Okay, and I'll bring this meter or this light bulb right here and drop it. Now I can go to the list here, okay, and go down and grab a meter and drop it in, okay, and then scooch my list back over because I don't want to use up this space. So let's bring this meter over like this, and now let's put the ohm meter. So I'm going to click on this, see it says voltage, but change it to resistance. See, now the R is lit up there for resistance. I'm going to connect this up. There's no polarity when it comes to resistance. Okay, so now I put this ohm meter right across that cold light bulb. Start simulation. Look, I get 48 ohms. I get 48 ohms. Well, that's not really too bad. The 48 is less than 48.039, correct? So I've got this right in the middle of the two values that we got by calculating with Ohm's law. When we put 3 volts, which is actually 2.94, we got 61.2 milliamps. And at that temperature, that bulb was 48.039. Now, you would expect if it was cold, it would be higher. So this may be a slight discrepancy. We're not going to argue the point. Now, see, it does show the light bulb lit up, which what's interesting is there is actually current going through that light bulb right now, even though you got an ohm meter on it. All meters that can measure ohms, resistance, it has to have a battery in it because it has to push electricity through whatever you're measuring the resistance of. Otherwise, it doesn't know what the resistance is. So interestingly, that bulb does light up a little bit. I wasn't expecting that. But anyway, 48 ohms, almost 48 ohms, right? Just slightly under. You would expect it to be less with 4.5 volts and 90.9 milliamps because it's hotter. So you'd expect it to be, the resistance to be lower than this. Okay, so there's a full demonstration of calculating resistance with, if you know the voltage and the current. Now let's do it the other way around. Okay, so we're going to go down here. We know it's 48 ohms roughly, right? So we're going to, if we're going to calculate resistance, it's volts over amps. Okay, and that's what we had done. Let's pick something else. Let's pick current and resistance to get voltage. So I times R equals volts. So we go down here, and the current is 0.0909 times basically 48, 4.36. See? So volts equals current times resistance. So our resistance was basically 48. I rounded off 48 times 0.0909 equals 4.36. So you see Ohm's law, whether you use a meter or Ohm's law, if you know two of the values, you ought to be able to calculate the rest. That leaves us, we calculated resistance, we calculated voltage. Now let's calculate current. So current would be volts divided by resistance. So that would be 4.36 divided by 48. 0.908. That's basically, you could make this 0.0909. It's just slightly different because I use 48 instead of 47. We'll try it with 47. 7.965. See, I got 0.90 rounded off to 9. So see, it matches. That was kind of an awkward go here for the first time, but this is enough for the first time with you and Ohm's law. At this point, you ought to be able to go into Tinkercad and create your own flashlight and do some calculations. Now, I want to cover one more thing here real quick. We won't need the calculator. I'm going to stop the simulation. I take this bulb, Control C, Control V, and I'm going to put it right here. And I'm going to take a wire from here over to here. This is kind of kludgy. And then from here over to here and to there. Okay. Now we got two light bulbs in parallel. Now let's start simulation. Now look, we've got even less voltage, right? In other words, I think we had something like 2.94 or something, I can't remember. But now we've got even less voltage, but we got almost double the current because we're drawing twice the current off of those two batteries. The batteries are in series, so when it's off, it's 3 volts. Let me make this a little bit more interesting. I'm going to stop the simulation. I will kill that wire. I'll take and I'll Control C, Control V, and I will put this switch right here. So now I can turn on the simulation and I turn on just one light bulb. Okay? So the other light bulb, it's in parallel with the first light bulb, the one that's lit, but it's got a switch in there interrupting any voltage going over there and resultant current flow. So we have 2.94 volts, correct? Watch what happens when I turn on the second bulb. See the voltage drop, the current increased. So the current is 61.2 milliamps. If we had double the current, it would be 122.4. But no, it's only 120. That's because our voltage dropped, because as we increase current going through the light bulbs and through the battery, the internal resistance that you can't see and you can't really measure, actually we could, but we're not going to right now. But that increase in current flow through the batteries drops some of that 3 volts internally in the batteries. It's called internal resistance. So this is a perfect demonstration of that principle. Now we're going to do one more thing. We're going to, just for grins, I'm going to stop the simulation and I'm going to delete these wires, and I'm going to put this light bulb down here. This is going to be more complicated. I'm going to have to move this one over because it's too close. And now I'm going to take and then run this wire down to here. Didn't like that. Yep. Just delete that wire. Sometimes they don't drag real well. So go from here down to here, and then we go from here up to there. So now we've got these 2 light bulbs in series. Okay? Start the simulation. Look at that. We've only got half the current that we had with one light bulb. Remember, we had about 60 milliamps with one light bulb. Now we only got 30. That's because the voltage divides across these 2 light bulbs. If I were to put voltmeters on each of these right here, you would see half of that voltage. And just to prove that, are you following me now? We've got 2 light bulbs in series, and they're each only half as bright as they were when they were in parallel. It probably would have been better if I would have kept the 2 light bulbs in parallel and then duplicated this one down below. I might do that later, but I want to hurry up and get this done because this is getting to be too long. Now what I was going to do was put that switch in there. So I think I'm going to stop the simulation. I'm going to bring this down here, over and up to here, and then I'll bring this one over and up to here. So now this switch will short out that light bulb. Okay, start simulation. See, that light bulb's off right now. And we got 61 milliamps because this switch is acting like just one wire that goes from here to here. See, it goes right through here and back to the battery. It bypasses or shorts circuit that light bulb. And now you see the current went back to 30 milliamps basically. So I could have done a neater job with this, and I might go back and do that later. But for right now, that's enough to get you started on Ohm's law. So remember what you were supposed to do. You were supposed to write down that triangle and the 3 equations, and then go into Tinkercad and play. So we're going to leave this right here for right now. Sufficient to the moment is the strain thereof. I'm going to go back and probably clean that up. I'm not going to draw it in front of you. I'll just go back and rearrange the circuit so it's easier to follow. Maybe when we start the next episode. But for right now, that ought to be enough to get you going. Remember, E equals I times R, I equals E over R, and R equals E over I. Draw that triangle and write out your 3 equations. Go into Tinkercad, create a little circuit, and play with it. Play with the meters. In the meantime, I'm going to be preparing another episode. Thank you.